The definition of exponential equations. As the name suggests, exponential equations are equations that have the variable in the exponent. For example, we have the following shown on screen. Are all examples of exponential equations, as all variables are in the exponent. Exponential equations have different methods of solution, depending on the complexity of the parts involved. In the following paragraphs of this tutorial, we will explain how to solve exponential equations from the easiest to the most challenging. 1. Exponential equations with a single exponential term. The simplest case of exponential equations involves situations where there is a single exponential term on one side, and the result on the other side of the equation, which is a power of the base number that contains the variable in the exponent. The general form of such equations, we have the following shown on screen. For example, we have the following shown on screen. This belongs to this type of exponential equation, as there is a single exponential term 2x on the left side and a single number on the right that is a power of 2. The first thing to check when trying to solve such equations is to try writing the result as an exponential number with the same base as the term that contains the variable. If you can do this, then you can forget the common base and focus only on the exponential part, where you obtain a type of equation usually linear as those we have discussed earlier in this course. For example, in the exponential equation, we can express the right side as 2 to the power of 3 instead of 8. In this way, we have the following shown on screen. Since the base is the same on both sides, so there must the exponents be as well. In this way, we obtain the following shown on screen. Example 1. Find the value of x in the exponential equations. A. 3 to the power of x equals 243. B. 2 to the power of 4x equals 64. Solution 1. A. Given that 243 is equal to 3 to the power of 5, we have the following shown on screen. Now, the bases are the same. Hence, the exponents must be the same as well. Thus, we have the following shown on screen. B. Given that 64 is equal to 2 to the power of 6, we have the following shown on screen. Now, the bases are the same. Hence, the exponents must be the same as well. Thus, we have the following shown on screen. Two. Exponential equations with more than one exponential term where all terms can be written at the same base. If the exponential equation contains more than one exponential part, the solution procedure may require some kind of factorization. However, if it is possible to write all terms at the same base, this is not a problem. Let's consider a pair of examples to illustrate this point. Example 2. Calculate the value of the variable x in the following exponential equations. A. 5 plus 2 to the power of 3x minus 1 is equal to 3 to the power of 2b. 63 minus 3 to the power of x equals 2. 3 to the power of x plus 1. Solution 2. A. At first glance, this equation seems to have two exponential parts, but one of them contains just numbers. So we can complete the operations to simplify the number part and write it as a power of 2. We have the following shown on screen. After having expressed both sides as powers of the same base, here the base is 2, we can focus on the exponents only. Thus, we have the following shown on screen. We can express 3x plus 1 as 3x. Thus, we have the following shown on screen. Factoring 3x on the right side yields, we have the following shown on screen. Thus, since the bases are already the same on both sides, we have the following shown on screen. Exponential equations where the variable appears in more than one term. As you see, the exponential equations are becoming more and more challenging. However, if you can express every term to the same base, it is still possible to solve such exponential equations through the standard methods, i.e. without involving logarithms. Let's consider a pair of examples to clarify this point. Example 3. Solve the following exponential equations. We have the following shown on screen. Solution 3. First, let's separate all terms containing the variable from the constants. Thus, we have the following shown on screen. Now, let's express all terms containing the variable at the same power. Thus, we have the following shown on screen. Factoring the common term 2 to the power of 3x yields, we have the following shown on screen. Again, first let's separate all terms containing the variable from the constants. Thus, we have the following shown on screen. Now, we express the terms containing the variable to the same base. Thus, we have the following shown on screen. Moreover, we can express 5 to the power of 2x plus 1 as 5 to the power of 2x. Hence, we have the following shown on screen. Solving exponential equations where the terms cannot turn to a common base. Now things become more challenging, as if the terms are impossible to write at the same base, we must use the logarithmic approach to solve these exponential equations. Obviously, the base of the logarithm on both sides must be equal to the argument of the term that contains the variable. Only in this way, we can eliminate the exponent from the equation. The simplest case would be when there is a single exponential term and a constant on the other side of the equation, but the logarithmic method can be extended further to include a wide range of exponential equations. Let's consider a few examples in this regard. Example 4. Solve the following exponential equations. We have the following shown on screen. Solution 4. We have the following shown on screen. The exercise is considered as solved in this form, as log 3/4 is a number that has a certain value. Indeed, looking at the calculator provided by us, we obtain the value of 1.26 when written to 2 decimal places. Hence, we have the following shown on screen. Remark. We can also find the value of log 3/4 by expressing it. We have the following shown on screen. We have the following shown on screen. We have the following shown on screen. Sometimes, the variable of an exponential equation is in the second power. In these cases, we must solve a quadratic equation when turning all terms at the same base is impossible, otherwise, we use the logarithmic approach. Let's consider a pair of examples to clarify this point. Example 5. 3 to the power of x squared plus 1 is equal to 9 to the power of x. 15. 2 to the power of 5, x equals 3. 2 to the power of x squared. Solution 5. First, let's write all terms at the same base. Thus, we have the following shown on screen. Now, we focus only on the exponential part. Thus, we have the following shown on screen. This quadratic equation has a single root, as it can be written in the form, we have the following shown on screen. Hence, we have the following shown on screen. b. It is impossible to write all terms of this equation to the same base. This means we have to use the logarithmic approach for solving it. We have the following shown on screen. Since log 25 approximately equals to 0.4, we obtain the following shown on screen. We can multiply all terms by 5 to remove decimals. Thus, we have the following shown on screen. We have a equals 5, b equals minus 25, and c equals minus 2. Thus, we have the following shown on screen. We have the following shown on screen. That is all for lesson 13.2.1. To continue this tutorial, please watch 13.2.2, Logarithmic Equations. Thank you for watching. Make sure to like and subscribe to keep up to date with new videos. For more information, calculators, and tutorials, please visit www.icalculator.com.